Okay, so here we're going to talk about the basics of how ionic bonds form. This is going to cover that last little bit at the bottom of page 5 underneath your covalent naming and formula writing practice, and if that's not quite done, that's fine. We'll have a day after we have our ionic focused day to practice and come back and make sure that our ionic and covalent practice are all filled up. So there at the bottom of page 5, it reminds us of some of the basics of our ionic compounds, and really when it comes down to it, we need to remember that that's a metal and a non-metal together, really reinforcing that because it's important. And these ionic compounds, those metals and non-metals, form ions, and because they're opposite types of atoms, metals form positive, non-metals form negative, and those opposite charges are attracted to each other and form an ionic compound. Now, we're not really getting into the name and formula writing stuff quite yet. We really want to focus on how these electrons are moving in order to create those charges. And so remember, with our ionic compounds, these pairings of elements have the biggest electronegativity difference. So one of those atoms is stealing the electrons from the other. It's strong enough to just pull them right off, keep them for itself. So they're not being shared. They're starting off on one atom and then they're moving to the other atom. And the whole reason these are being transferred and moving from atom to atom is the octet rule. Every atom wants to have 8 valence electrons, and they're either going to lose or gain to get to 8. Now, it's a little bit weird, and I'll remind you later how weird it is that electrons can be lost to get our atoms full and get to those 8 valence electrons. So if you need a reminder why that works or how that works, please let me know, and I'll help you out with it. But the kind of simplest thing is just to remember that they can lose or gain. So at the bottom of page 5 are where we're going to have our steps for how to do this process, and the steps that were written there were not correct at all, which is why I either already have or can and will give you a little yellow piece of paper with the correct instructions all written out. So you don't actually have to write all of this down there. I'll have a kind of short summary on the next slide so we can use it while we're doing this. When you come to class next time, I can give you that little yellow sheet of paper. If you would prefer to write all of this down on your own or type it out, print it out, and then tape it over those old instructions, that's exactly what we would be doing with this yellow paper anyway. So let's get into these instructions. They're really just 3 steps. Don't let the bullet points fool you. Those bullet points are just to clarify and add a little bit of information about how we do each of these steps. And I'm actually going to kind of work out this very first example as we are doing this. So you don't necessarily have to be looking at these instructions on the yellow piece of paper here because you can see them on the screen. You might as well go ahead and flip to the top of page 6 and start writing out this example and following along with that as I'm doing and going through them, because I want you to understand these steps, and I think the best thing to do is to talk about it and understand what all these words means in the context of an example. So we'll come back and do this next problem here in just a moment, but I want to help you understand these steps by applying them and actually doing them. So step number 1 is to draw one Lewis dot diagram of each element. So if that's between sodium, Na, and chlorine, we need to first know what the symbols of those elements are, and then we need to figure out how many valence electrons they have, because each atom, each element gets 1 dot per valence electron. So looking at our periodic table, we can predict the number of valence electrons for every atom on the periodic table based on what column they're in. So our first column, where our sodium is going to have 1 valence electron. The second column, those alkaline earth metals, have 2, and then 3 over on boron's column, and then 4, 5, 6, 7, and 8, all the way to our noble gases over there. So the 2 elements we care about are sodium and chlorine for now. So sodium has 1 valence electron and chlorine has 7. So now as we're placing these dots around our atom, remember that each side, and it's kind of like a little invisible box with 4 sides around our elements symbol. Each side needs to get 1 dot, 1 valence electron, before any sides pair up. So sodium, we just put a dot. It doesn't even matter which side it goes on, remember, as long as it's just on one of those sides. Chlorine, I'm going to demonstrate how, because it has more than 1 dot as we start placing them, I have to put 1 dot on each side before we go back and double up. So if I did have an atom that had either 4 or 5 electrons, they would be arranged like this. Then my 6th gets added here, and then my 7th there. Really important that we have 3 paired electrons and 1 unpaired electron. It's a little lonely electron, and there's this kind of empty space next to it. We need to be able to very clearly see all of the electrons and all the empty spaces that don't have electrons in them here. And that's important because in this next step, we are going to be drawing arrows to show how our electrons can move until all of our atoms are completely full and empty. So we're going to be moving these electrons, these red dots, with arrows, and the arrows need to start at a specific electron and point to a specific spot. Now, we're going to, I know it says moving from nonmetal to metal. Technically, it's metal to nonmetal. I have that backwards there. But even on top of that, I don't even need to think about it because we're going to try and have the least amount of movement possible. So instead of moving all 7 of these dots over to our sodium, we're just going to move this 1 dot here over into this empty space around the chlorine. So I'm going to have my line, my arrow start here, and then it's going to end pointing directly at that empty spot on the chlorine. Now, this worked out perfectly. All of my atoms, if this is kind of our plan, and when these electrons do move like this, then sodium will have no more electrons visible. It looks empty, and our chlorine is going to be completely full. That is our goal. But it's not always going to happen with a single arrow, and sometimes it's not even going to happen with just a single sodium and chlorine. If we run out of electrons or empty spots, we need to draw another atom to get what we need. And the easiest way to kind of explain this is if sodium did have 2 valence electrons, if it had 2 dots here, after I move the first one over, then chlorine is full. I have no more empty spaces to put this other electron. So sodium isn't completely empty, even though chlorine is completely full, which means I need another spot. I need another empty space. And so what we would do in this situation is draw another element that has an empty space, which means draw another chlorine to get another space so we can get all of our atoms completely full and empty. And as long as that chlorine still has the same 7 valence electrons as the one that we drew before, then it's perfectly fine to just draw another one to get what we need. So, sodium doesn't have 2 electrons, which is why that's not actually happening, but we will see that in some of our other examples. And never be afraid to just draw another one of the exact same thing, either one, depending on what you need. And then once all of our atoms are full and empty, we're actually going to redraw the same atoms, the same elements, sodium and chlorine, with their new electrons. So now sodium has no visible valence electrons here, and chlorine is completely full with 8. Then we're going to put those atoms in square brackets. It's really tiny there. It's really easy to do, but it's also really easy to forget. We just put big square brackets around each of those final versions of our atoms. And then we need to put the charge in the top corner. That top right corner is where our charges belong. Now, the charge is the same charge these elements always have and always will have, but we can either remember it from the periodic table, or we can remember that sodium, because it's losing 1 electron, and losing electrons makes us positive, is going to be a positive 1 charge. Because chlorine is gaining electrons, that's going to make it negative, and because it just gained that 1 electron, that's negative 1. So that is our process. It mentions using coefficients, and I'll show you how to do that if I did need to have more than one atom. Like, I guess we already saw an example where I might have needed 2 chlorines. Then all I would have to do is add a little 2 here instead of drawing them out separately. But we'll see some more of those more complicated examples where we have to do more of this later. So let's go ahead and do another example following these same basic steps on the next slide. Remember, hopefully that example I was just working out, showing that process of forming the ionic bond between sodium and chlorine goes right here. And that whole thing is our process. We need all of that, the red and blue stuff, as well as this purple stuff that was at the end. All of that is our process and part of our answer. So let's do it again for a different couple of elements. I have those abbreviated steps, just the 1, 2, 3 there at the top to remind you of the basic steps, and I'll remind you of some of those other pieces of information as we need it. For right now, we're just going to start by drawing one Lewis dot diagram of calcium and sulfur. So calcium is Ca, sulfur is S. And I need to add dots around these. Calcium's in the second column, so I'm going to put 2 dots around them. And then sulfur is in column 16, so it has 6 valence electrons. That's 4, 5, 6 dots. Drawn those Lewis dot diagrams. Now we're going to use arrows to move our electrons, and each individual electron is going to move, and the easiest ones to move, the least number of arrows, is going to come from the calcium to the sulfur, filling in these 2 specific empty spots there. And now all of our arrows, all of our electrons had a place to start and to end, so that worked out rather nicely. Just needed 1 atom of each type, and so we can redraw these. Calcium is empty. Sulfur is going to be the one that's full since it got those 2 electrons. We add square brackets and their charges. Here, because calcium lost 2 electrons, it's a +2, and sulfur gained 2 electrons, so it's a -2 charge. Hopefully this isn't too bad. We're going to make it a little bit more complicated in some of these next problems, but not too much. It's the same basic process. Let's start with our elements. So we've got K for potassium and O for oxygen, and K is in that first column, so it gets 1 dot, and oxygen gets 6. So we've drawn our Lewis dot diagrams, and now let's start with some arrows. I can move my 1 dot from potassium over into that empty spot right next to it on the oxygen, but we're not quite done because oxygen still has another empty spot over here. It isn't completely full, so even though K is completely empty, we're not quite ready to redraw our atoms. We're not ready to move on to the next step. So what we need to do here, because we need another electron to help fill in this space, is to draw another K, another potassium ion. Because that has our electron on it, it can get moved over into that space, and now every atom is completely full and completely empty. We just needed 2 Ks to make it happen. So remember, when we redraw all of our atoms with their new electrons in them, we can just use this 2 over here instead of drawing out 2 Ks. There's not any dots, so it's not too complicated just to draw 2 Ks, but it's fine. And then don't forget to draw the square brackets around each of them and give them their charge. So it doesn't always work out perfectly with just 1 of each, but it's not too complicated to just add another of a different type. So let's look at this next example. So our magnesium is Mg, F is our fluorine. Finding their valence electrons, magnesium gets 2, fluorine gets 7. As we start to draw our arrows, that first electron from magnesium's got a spot on fluorine to fill in, but the other electron doesn't. Fluorine's all full, it's got 8 electrons, it's got no more empty spaces, but I need another empty space. What do? I need to add another fluorine to get another empty space. So with 2 fluorines there, I have a space to put that second electron in, and now all of my atoms are going to be full and empty once I kind of follow this plan and move my electrons. So we're ready to redraw these with the electrons that they have. Remember, you can use that coefficient instead of drawing 2 F's with all of those dots around them. Then just don't forget your square brackets and your charges. Since magnesium lost 2 electrons, it's got a +2 charge. Each of those fluorines only gained 1 electron, which is why it just has a -1 charge there on each. As we move into this next 2 examples, I'm going to actually have you do the 5th example on the page for yourself. It's not quite as complicated as that last one, so I want to do the last one with you just to kind of show you the worst case scenario, the most complicated possible example, but it's still technically the same process. It's just a little bit more work to write out. So as we're looking at these elements, it's talking about showing the ionic bond formation between barium and nitrogen. So barium is Ba, nitrogen is N, barium gets 2 dots, nitrogen gets 5. If I start trying to move my electrons over from Ba to nitrogen, I've got a spot for both of these electrons to go into, but now nitrogen has an empty space that I don't have an electron for. Well, that's easy. I can just draw another barium. Draw it over here with its 2 dots so that we can get those spaces filled in. But, oh wait, there is only 1 more space available. So now that I've added this other Ba, I have an extra electron here that doesn't have a home. It doesn't have a space to fill in. So at this point, I need another nitrogen. So, okay, that's fine. It's, not quite what I was planning, but we can make this work. Nitrogen needs 5 dots around it. And, now I have some empty spaces. I can move this electron over onto this side, so I have a pair of electrons here. But shoot, I've now got some empty spaces on this nitrogen that aren't getting filled in. So empty spaces means I need more electrons to put in these spaces. And right around here, you might be doubting yourself and whether you'd done it right, and maybe that would have happened already for you. But we gotta keep going. Follow this process. I promise we are almost done. 1 more barium with its 2 valence electrons is finally going to give us a place to put all of our electrons and have all of our spaces filled in. So I know my drawing is a little bit of a mess with bariums and nitrogens everywhere, but if you look, every single barium is empty. Every single electron has a place it's going to be going. And if you count around each of our nitrogens, they are going to end up with 8 valence electrons. They've each got 3 arrows coming to it. So they started off with 5, and they're going to get 3 more each. So every atom at this point is going to be full or empty. And as we start to write out that final version, this is really where those coefficients help us a lot. We ended up needing 3 completely separate barium atoms. So I'm going to put 3 Ba here, and 2 nitrogen atoms, which ended up with all 8 valence electrons around them, giving those square brackets and their charges. Bariums each lost 2, so that made them a +2. Each of the nitrogens gained 3, so that made it a -3 charge. So, like I said, that's kind of the worst case scenario. As complicated as these can get is when our charges, our electrons, are big numbers but not equal. So we'll talk a little bit more about how we can kind of predict how many of each of these we'll need. And you might have already started to see that pattern forming with the charges and the electron numbers and some of these coefficients that we've been writing. So if you do see a pattern, then use it as you're finishing out that last problem that I skipped over. If you don't see it yet, just follow these steps, 1, 2, 3. Try and finish out that problem if you want to be able to get a stamp. And then in class, we will talk about kind of a shortcut we can take to figure out how many of each we're going to need.